First, I have to say thank you for being here. Christian told me or asked me already, I think, 4 or 5 months ago, if I would be willing to give a presentation about some ideas for realization or application of identification codes for post-Shannon theory. I said instantly, yes, I do. And what's coming now is, I would say, not a scientific talk, right? It's an ideation talk. So it's just ideas out of brainstorming, with different colleagues, I would say, on special projects. You see here the names, So most parties are from TU Munich, Holger, Johannes, Waffa, Labidi, Christian Deppe, Frank Fitzek, Juan Alberto Cabrera, myself. In my primary role, I'm actually dealing with quantum networks. So I'm a systems guy. As we learned yesterday, and we are participating in all the projects on the right side. But when Holger actually 4 years ago dropped into my office and was showing me all these nice results out of Post-Shannon theory, wiretap codes, jamming, blah blah blah, in this information theoretic way, there's one thing that stuck to my head, which is identification, exponential increase in channel capacity. When you work for a telco provider, this rings a bell. So because network expansion, for instance, is one of our biggest pains. Costs tremendous amount of money to introduce new networks with higher bandwidth, lower latency, and all that kind of stuff. And I decided for myself, although it's not my core topic, to somehow stay online and discuss this further. And you see some results. That's in principle the core message that got stuck with me. I mean, when you talk about identification, I mean, you have the usual setting that you've seen a couple of times already yesterday by Frank Fitzek. You have a message, you have an encoder, a noisy channel, and a decoder. And in identification, the special thing is that the decoder is only allowed to ask a yes or no answer, or to get a yes or no answer. So in principle, has this message been sent by the sender? Or was this message assigned for me? Yes or no? Is the soldier on the battlefield dead? Yes or no? I think this was one of the first use cases, as I learned. And this gives you exponential capacity increase if you utilize randomized encoding. So you use random numbers. Normally on these conferences, I'm always, let's say, speaker number 3 or 4 on a line of identification presentations. Then all the basics have been said. So that's why I don't have a slide on that. So now I'm actually the first one of the day. So I can only recapitulate this orally. So it works in a way, at least in a linear code, that you design a code book. You have identification messages as lines. You have blocks of bits on the columns. And when you actually want to send an identification or encode an identification message, you encode it randomly. This means you have a random number generator, that gives you, let's say, a number for the block. And then you send a hash or whatever of that block to the receiver and the number itself. And the receiver is then checking on his code book, does the same operation as the sender, and then can decide if the message is decoded yes or no. Which means, was the message for the receiver yes or no? You can improve the scheme if you have common randomness on the sender and receiver side, because then you don't have to send the index. And then it's actually, if you then use appropriate coding schemes, not linear codes, but these Reed-Solomon or Müller codes, then you can go up to the, I think, the exponential information theoretical limit. That's how I understood it. I hope that's true. But at the end, the figure of merit is this double exponential increase in channel capacity, which means for me, a double logarithmic shrinking of message length. And this makes it so attractive because you can argue whatever you do. I mean, it doesn't cost any bandwidth. It's in principle for free, if you like. So what's the impact? So I just created a slide. The first one I already told, it's network expansion costs, which is the striking argument. If you could actually shift all your traffic that you have now into post-Shannon communication, you would have a linear network expansion you have to carry or realize if you deal with exponential data increase. Doesn't work, but on a paper, first thought, this was a triggering thought, but it gives you scalability of your spectrum. So because you can actually try to offload, hopefully, some traffic into that scheme, which then will then become a lot cheaper. And maybe there's control plane efficiency, that you can use if you use broadcasts into your group of clients. We'll look into this on an example basis later, and maybe there's even strategic impact for, let's say, strategies where you actually try to use or employ identification into control systems for your networks. Maybe that works out. Coming also later to that. So the first question, after in principle thinking a lot, try to summarize what prerequisites makes a good identification use case up to my mind, or our mind. It works best if you assume a broadcast channel, right? I mean, it's a one-to-many communication or a many-to-one communication. Many-to-many might not work so good, because you don't know the relationship among the parties. But in this way, it seems to work quite okay. You need, if you want to do randomized encoding, you need shared randomness in order to get the messages as small as possible. And I mean, you see now here an example for a one-to-many communication. You always have to somehow find a setting, where the number of positive receivers or receivers that identify positive is rather small, compared to the complete number of receivers in the set, because the codes get most effective then. And it has to do with this type 2 error that I have not introduced, but maybe you're talking yesterday morning about that. Type 1 error was in principle the error of, let's say, imposed by a channel. The type 2 error is a misidentification, where you actually expect a yes, but you get a no. If you have a broadband channel, you're pretty good off, because then in principle doesn't matter, if you send in a couple of additional short messages into the channel. But the scheme also works on a broadband channel, So the more precare in German, so the shorter the bandwidth, the smaller the bandwidth, makes communications possible, that might not be otherwise possible. Coming back to this later as well. The communication scheme must cope with this famous type 2 error. This means putting a nuclear missile on an identification system is not a good idea, because there can be misidentifications. So the scheme has to cope for that. It doesn't have to affect the overall performance. And encoding is fast. Decoding is elaborative. So encoding, I mean, Shen or post-Shen, I understood it's the same speed. But decoding, since you do this hypothesis tests, and you allow for multiple identifications, so you have to do multiple identifications on the receiver side, you have to do this iteratively or in parallel. But this takes time and this takes energy. And that's the downside of things from my perspective, because the gains that you get on the communication channel, you might consume with the time and effort you need on the decoding side. But let's see. That's also for me, in principle, the final open question. So where is this break-even point in this communication scheme? Last but not least, there's K-identification, where you actually can have a scheme that allows not just for a single positive or negative identification, but for a group. This might make more effective implementations later on. So let's go to the use case types I want to talk about. I brought 4. Number 1 is monitoring. I think that comes rather fast. So you principally ask, is this monitoring message for me? Did an event occur? Yes or no? Number 2 is special purpose data storage. If you turn the scheme around, you can actually compress data, or you put less data into your storage on the price that the storage cannot give you all the information. Just can answer dedicated questions. Number 3 on the top, we all know joint sensing and communication. Joint communication and sensing. Here's maybe another abbreviation that comes into play. We named it joint sensing and identification. It's somehow an interplay about sensing, and these identification messages, to create action. If a condition is sensed by whatever, by the control system, by the robot or whatever, yes or no, then conduct an action. And last but not least, there's semantic communication, just like the talks before. You might use this scheme for. I show you an example for each of the 4 items. So let's start with monitoring. That's a not so easy use case, I would say. So the idea is to create a high-speed disaster recovery system, without the need for a control office to interact. This should be good enough, to just work automatically. It was inspired by, I don't know, earthquake detection like Turkey, an earthquake disaster like Turkey, or this flooding in the Ahrtal. And we are now somehow thinking a little bit in the future. And we assume a world where, let's say, you have earthquake detection or water flood detection system on every square meter on ground. So it works. I mean, this must be a you have to assume that, an assumption, because if you don't have these many sensors, you can do it classically, with a normal network. But let's say if you have, let's say, so many sensors, then you can assume it's maybe too elaborative for a network provider to record all the sensors, and you might offer a broadcast communication channel to this sensor system in order to receive sensor messages in case of occurrence. Okay. So the encoding would be in form of geolocation. So I assumed here, let's say Germany has 3.6 and 10 to the 11 square meters. The Ahrtal as a disaster or monitoring area has 85 million square meters. If you now assume, let's say every 10 by 10 meters a sensor, this would mean 10 to the 5 sensors you have to put into the ground. And now you try to assume or to calculate how many bits you need for a communication message. In the asymptotic limit, you come up with 3 to 4 bits. It's always astonishing when you say that. In reality, you might need a couple bits more because you have let's say not a finite block length. But you stick with very little bits, number of bits, in order to identify the sensor in this setup. Now it works in a way in case of warning. Like water is coming or Earth is actually shaking. The sensor is sensing a post-channel coded message on a broadcasting channel, either peer-to-peer in a sensor network, or you just hook into a broadcast channel of that 5G, 6G network. The decoder is sitting at the base station. And you remember, decoding costs energy, right? But if I'm on a base station, I have enough energy. And I could think of a large server that is able to do parallel decoding. So the messages are coming, you start decoding. If it's not an alarm, you say, okay, I get a couple of yeses but mostly no's. If there are any messages coming, you actually can suppress them. But if there's something really happening, you get a flood of these messages. And you think about a discriminator level. If you get more than 10,000 messages, you ring an alarm because then something going wrong. And the alarm is not just anything. You hook this into a cell broadcast. That's the idea. That's a new disaster recovery system in Europe, I think, at least Germany. And the people get warned instantly when the disaster is happening. The earthquake wave is running through. In principle, within a second, you can actually launch a alarm message via cell broadcast. Would be possible. Johannes, he did a calculation about if it works in a mobile network. You assumed a random access channel, calculated the number of messages that would appear when an earthquake is running through, and I mean, the error probability is 1 over 5,000 in this 10 by 10 meter. So it works. Yeah, it would work. So the capacity of the mobile networks is large enough. So,
sorry.
Yeah.
So encoding takes the same time, whatever, than regular channel code.
Yeah.
Decoding is more expensive. So what's the gain of using that over classical communication?
Yeah, the gain is that you have we're sitting in a world where I have to govern, let's say, 1 million sensors with 10 cell towers. That's not possible at the time being. Yeah, it's not possible. I mean, you don't want to govern that many customers or user devices in your cell. You must make your cell smaller, because all the control messages that you have to do. I mean, it doesn't work with the cells at the current sizing anymore. This would impose a lot more investment into networks from the provider side, and by doing it this way, you could leave it more or less like it is. Yeah, that's the idea. Okay, small databases. Let's assume the following use case. Yeah, the provider wants to offer a service where, let's say, all customers of T-Mobile are actually put in the database every minute in what cell they are. It's a data privacy disaster. Yeah, don't get me wrong. Nobody's doing that. Yeah, it's forbidden. Yeah, but with the Porschen way, I think we could do it. Yeah, because this database could only answer a single question. Yeah, was the customer at time T in cell 4711? Yes, no. Yeah, and you cannot scan. Yeah, you cannot profile. And the API could, in principle, limit to 10 queries per customer per day or so. Yeah, so I would say that's data privacy safe. If you ask yourself how big the database is, yeah, I mean, I plugged some numbers. So we have 115 billion customers. We have 5.3 times 10 to the 5 minutes per year. Yeah, this means about 79 10 to the 12 data records. The number of cells we have is 2 times 10 to the 5. So in principle, we have to encode 15 times 10 to the 18 data records, if you like. And now you do a calculation with a log, and I mean, it comes out that in the classical way, you need 8 petabytes. In the Porschen way, I mean, you stick with 500 terabytes. 500 terabytes fits into a, let's say, single 19-inch housing. 8 petabytes, you need, I think, 3 racks or so. Yeah, that's tremendously cheaper. Yeah, and you solve a data privacy issue. So this might be a use case, right? Then we come to joint sensing and identification. I want to introduce Smart Dust. Yeah, that's actually the best example that we found on the internet. Smart Dust is an innovation, I think, by Berkeley. Yeah, they tried to make a fully connected device as small as possible. Yeah, and they came up with, I don't know, microns, yeah, 50 microns by 50 microns. It's a fully connected device. It's light, yeah, it doesn't cost anything, has a little energy budget, can communicate. That's pretty cool, huh? It's called Smart Dust because you can think of it like you take 2 hands of it and throw it up and out, yeah, and they go with the wind. Don't know. A little bit scary, but maybe reality soon. Yeah, so you can think of lots of applications. Yeah, they're small. If you ask for common randomness, yeah, could be done via sensing because they have a sensor also on board. Yeah, sense a common item, and then let's take a look into examples. They're a little bit more futuristic. Yeah, I think of let's say an agriculture use case like seed sowing. Yeah. I mean, you put some seeds into that robot, yeah, and you actually only 5 minutes. Okay, so 10 minutes. I follow my speaker in the morning. I mean, you let them out, yeah, and they're all in the wind, yeah, and then in principle, you don't have any contact anymore, yeah. They're only listening to a broadcast channel, yeah. That has to be available, but let's say they listen to all the mobile networks around, and they only listen to this identification message. You sense the environment, temperature, humidity, rain goes up to a certain level, and then you fire them off, yeah, from a central control center. Now every sensor in region, in this geo coordinates, yeah, get it out. The seed. Yeah, could also be poison. I don't know. It is terraforming, right? I mean, sand flies, yeah. I mean, can be in the atmosphere. Yeah, so it's up there. You couldn't put chemicals out, yeah, or maybe they screen the sun. I don't know. That's a really very interesting one here, the targeted cancer treatment. Yeah, and we had this in the morning. Yeah, I mean, you inject micro robots. I think 50 microns by 50 microns is still a little bit big for that. Yeah, but imagine you inject the robots; they are flying through your veins, and you have cancer. You know where your cancer is. Yeah, you have to know this. Yeah, and these micro robots, they drift to your cancer and then inject the medicine right there where it's needed. Yeah. To do so, I mean, you have to communicate with them. You have to know where they are. That's all a little bit tricky still with common technology. Yeah? So maybe I skip this now from here because not so much time. Randomness distribution, very quickly. If you want to get the exponential gain, I mean, you have to do randomness distribution in order to use it for your codes and your decodes. My company built a distribution server for that. Yeah? So we can do this now. Distribute entropy on a megabit per second, yeah, into the network, perfect for tests, right? In reality, I mean, you can also use the noise of a communication channel, maybe, or you sense it, yeah, just like the idea on the joint sensing and identification scheme. That's another one. We ask ourselves, can we somehow get this into control system of mobile networks? I mean, at the time being, you don't. Yeah, I mean, it doesn't make sense, right? I mean, we have every customer in our HLR, VLRs, yeah, so we know where they are. We can actually communicate with them. Yeah? We can control them, so no need. But let's think of a future setting where we have a cell and there is a million of these IoT sensors in there. Yeah? And we want to somehow manage their communication. This is where you have to think about. Yeah, so very futuristic. Lots of IoT out there. Yeah, wearables, cars. Maybe some sensors in the ground, on the light poles. I don't know. Yeah, very, very many. And we don't. The pain has to be so high. Yeah, the network provider would have to make the cell so small. Yeah, with so great investments that they start thinking differently. So they don't care anymore. They say we take the data from the IoT sensors, this couple bytes, just with us. We don't care. Yeah, so don't register. Just send. Yeah, how could this work? Yeah. So in principle, maybe using for sharing communication. Yeah. So let's think of a cell and everybody is silent. Yeah. So you don't have noise. This must be a prerequisite. Yeah. And let's say there's now a pencil with a self-driving car coming along. Yeah. And the network is actually assigning lots of bandwidth, yeah, to this single customer, but there's some spare. Right? And the spare could be used to pick up, let's say, the data from the IoT sensors. How does the IoT sensor know? He should not just, after having done his measurements, contact the network and say, I have to send something, produce noise. Now he just says silent. And when the beam comes along, the network knows that. And then he's using, let's say, post-channel communication messages on a broadcast channel to all the sensors, yeah, coded with geo coordinates. Now, let's say sensor sitting next to the street, yeah, in 5 seconds or in 1 second, the high capacity beam is coming. Get ready, yeah, and then he sends his data. Yeah. You want to ask questions or you want to hear more? I have to tell you this one. That's semantic communication. It's actually my favorite. Yeah. High frequency trading. That's the big money use case, right? I mean, between Frankfurt and London, 8 companies built RF, direct line of sight channel, to beat fiber. Use RF, really 20 hops, yeah, short wired, in order to be 5 milliseconds faster than a fiber connection. Yeah, 8 companies, that's big money in the game. Yeah. Now we come with semantic communication with post-channel theory. Yeah. We're shrinking 100 bits for a JSON into 10 bits of a post-channel communication message. You're faster. Yeah. You just use the old line, you're faster. if the decoder is fast enough, right? I mean, you see a decoder design, it's parallelized. Yeah? I mean, you get the Gaussian communication here at the receiver side. You split it up in a broadcast, and you have a cloud infrastructure that has, let's say, 10,000 of these decoders sitting there, just waiting to decode the broadcasting message. Yeah, and then if one of the decoder that stand for an action, yeah, that you have to define by your codebook. Yeah, ID1, sell 100 IBM stocks. ID2, buy them. ID3, do the same with Google. If they say yes, trade. The big missing thing in my thinking, actually I wanted to do this with Christian, but he got sick. What is the error? Yeah, what is the expression for the error that you still do? Yeah, when you try to, let's say, encode 1,000 of these trade transactions into, let's say, 10 bits. Yeah? There must be a percentage, yeah, that comes out. And this is what you need to know before you go to such of these high frequency trading companies. Yeah? Let's see, maybe next conference. And I stop now, right? Just to pinch that, yeah. You know what this is up there? That's a military sender. It's Raudafin. 130-meter high antennas. Yeah, they do long wave. Yeah, you can look up in the internet. Yeah, they broadcast 800 kilowatt, 14 to 50 kilohertz, 200 bouts on 4 channels, fully encrypted. Yeah, they do it for military communication to submarines and everything worldwide. Yeah, it's worldwide reach. Now think about identification in such a context. Yeah, I mean, 200 bouts, yeah, let's say 200 bytes per second. I mean, you can send 20 identification messages at the same time, fully encrypted. Yeah, and you have this receiver someone doing something, maybe stock exchange. I don't know. Yeah, I think it's a pretty good idea to reuse that. Yeah, or use it maybe for military purposes. I don't know. There's Radio Mundial in India. Yeah, I mean, this is the only country that has middle wave rolled out, yeah, as ITU standard over the country. They also have broadcast channels, right? There's also room for applications. They can interconnect, yeah. I mean, you have, let's say, a sender here doing long wave or middle wave, and you have at the BTS stations, you have a receiver. They're just this size. You just plug them on the tower. Yeah, and you bridge them into the mobile network. That's it. Thank you.
Thank you, Dr. Geitz, for your nice presentation. Are there any questions?
Thank you for the very interesting talk. So I wanted to ask about what do you think about the possible roles of quantum technologies? I saw quantum random number generator on one of your slides, and what do you think? Can entangled states play a role, some role here?
I mean, I have to actually forward to you guys. I know that you don't have the double exponential increase in quantum world. Yeah, so it's only. This behaves like classical, so only exponential.
Ah, so no double exponential increase, right? In quantum.
Well, okay.
When you want to identify classical informations over quantum networks, you also get doubly exponentially large codes. But the quantum number generator, a quantum random number generator, is this different quantum effect that's just useful for identification because you need common randomness to transmit the messages. So when the identification code is basically you hash your message with a random seed, then the question is, how good is your randomness? Because it's crucial for the performance guarantee. So the performance guarantee is as good as the randomness is. And then when you have a good random number generator, that's also like using quantum for identification.
Can we use entangled states if we need common randomness? So quantum random number generator is local randomness.
Yeah, but the
yes,
point
but
is,
there he's the expert.
Yeah. Okay, the point is what I understood. This randomness can be public. Yeah,
can be or cannot.
Can. That's why we can also send them. Yeah. Correct? Yeah. Yeah. and the other rates are much too low. Yeah.
Okay, I'd like to connect to my first question. Say, in this monitoring scenario, that's massive activity detection, which we tried to do for a while, and we have unsourced random access, which is also a solution to it. So where is identification better in this scenario? What's
shorter messages, smaller messages, logarithmically smaller messages, and then in principle, no problem with the other communication in the cell. I mean, you assign, let's say, a small fraction of your bandwidth to the broadcast channel, yeah, and this is enough for that scheme, yeah. Whereas when you use classical communication, I mean, you probably overload or you use your entire cell capacity. Yeah.
So comparing identification with unsourced random access rings a bell with me, because I thought that K identification, so where you have K sets, has a similar mathematical structure that could be useful for, like, to use those codes actually for random access protocols. However, I noticed that, like, the philosophy is very different. In identification, usually one looks at worst case guarantees, worst case over the messages and so on. Or so for example, also guarantees for every K set of senders maybe that are active. And in unsourced random access, you have actually a very strong averaging assumption that the performance criterion is only on average over the active senders. So, which makes actually a trivial code, just picking one code word at random, better than something based on K identification. But this is just because of the performance criterion. So I think it's very important to look at what actually is the performance criterion that I have, and is such an averaging criterion sufficient or not?
Okay.